have going on here, so let's check this out. Oh, we have this index monad, and let's review this real quick. Right, so the index monad thing is just about getting all these dimensions to match, and I gotta remember what these dimensions mean. I think it's like something about preconditions and postconditions. So yeah. Yeah, so it's all about preconditions, postconditions. Okay. Then I think we have some stuff in here. Excuse me. This complained about this before, but I think it's fine. Am I supposed to put this in backticks? Because this is just H-Link complaining. Oh, I gotta send a tweet. I forgot about that. Tweeter. Building indexed monads in Haskell via thinking with types Twitch TV. Ow. Boom. Okay. I gotta shut this door. Hodor up here over us and give us point free powers, hopefully. And there we go. Okay, so what are we doing? So, what's SIO? Just system IO. Open file. So we're just wrapping this, and I think what we're doing is just making sure that the what are we trying to do? I don't remember what linear is here. Like, what does linear mean? That's what I'm trying to remember. And then once I remember, hopefully this will be okay. So this linear state exists solely to be used as a data kind. Oh, right. This is about using some resource once. So we're emulating the linear type system of actually I don't remember, we had an example of linear type systems before. What was it? Idris? I think that's the one. Anyway. Okay, so S has to do with this ST trick stuff, which I don't exactly remember what it is, but it has something to do with making sure that you can't call, like, anytime you have an open file, it has to be on a different thing, and you can't compare them or something. Okay. So at 1, we say this function can be used for any next and open. However, the post condition of open file is that next is incremented. So that's the post condition. And that we insert next into the open set. Insert next into the open set. So this is the post condition. The post condition means so this is, gosh, this is tricky for me. So I think so we can take a linear state of any precondition and any post condition, as long as the result of that computation is something whose precondition is this thing plus one and open contains next, I guess is what that means. And again, this is only happening at the Freeman. Thank you for the host. I don't know who those two chatters are, but I think they're bots, but it is what it is. Hello, and I also noticed there's two folks watching, so hello, how are you this evening? Or, well, it might not be evening where you are, but it is where I am, so good evening. Okay. Anyway, so I think we're okay there. And then open file returns a lifted handle whose identifier is next. The handle itself is tied to the linear, this S here, via the st trick, the S parameter. The handle type itself isn't very interesting either. It's simply a wrapper around system IO handle with the two phantom types specified by open file. Yeah, we define this here. So we have two phantom types, one for this st trick to bind these two things together, and then the key, which is again only necessary at the type level. Okay, so in order to define close file, we'll need machinery to determine whether or not a handle is already open in the open set. Whether or not a handle is already in the open set. This turns out to be quite straightforward first class function. We know first class functions. We can just say type is open. ZT. Key K TS list of key K. What's up, Bloomy? How are you? Filter not tie equal key. Oops. Key. Beautiful night. Oh, that's great to hear. It's actually pretty nice here too. It's a little hot right now. The temperature got up in US again, so it was like 90 degrees today. Are you a Fahrenheit? Probably. I don't remember where. Anyway. 32 Celsius. Yeah. So that's how hot it was today. It was pretty hot. Okay. 13. So 25 is... Yeah, so 25 is 75 Fahrenheit. So that kind of gives me an idea usually. That's usually how I do that math. So, yeah. That makes sense. That's not bad. I wish it was that temperature here. That's about the temperature I like. Okay. So this thing is just to say, like, is the file already open? That's what that is. because if the file is already open, we shouldn't open it again. Then we have a close, which is probably going to remove the thing somehow. Is just find tie equal key, yes. Okay, so I should probably explain these things again for those who don't remember or always forget, because, you know, it's really me that's, I'm not forgetting, but it's easier to just remember if I say it multiple times. Anyway, this operator, sort of flip Kleisli, is basically composition at the type level, and flip bind is like $. So yeah, apparently these are like, I mean, right now what we're doing, my understanding of what we're doing is we're generating a linear type system, essentially. So, you know, if you open a file, you don't want to open it a second time, and when you close a file, you don't want to close it a second time. So we're basically just handling our resources. So it makes me feel like I'm back in C++ days, I guess, but I don't have to remember to close my file. I don't close files in Python anymore. I just use with clauses. So anyway, so yeah, this one is just gonna go find the thing and make sure it exists. Although, how does it? I think so. I think that's the point. So you can say things can only be used exactly once. I think that's how this works. Now, right now we're building specifically, you know, we're building specifically a linear type system to handle files, but I don't know. Yeah, that's exactly what I was just about to say. I don't know what the limitations are yet, so I don't have too much to say about it. Yeah, let me just show you this, just so you see it. Oh, nope. So basically, you have this new type that essentially defines like preconditions and postconditions. So you know, your postconditions, I mean, it doesn't matter what these things are, as long as somehow they simulate what you're trying to accomplish. So what we're trying to accomplish is that our you know, our postconditions are that if we open something, you know, that is part of our postconditions, so that you can just say, like, you know, if you already have this thing open, then I guess it's no good. Shouldn't this be is closed? Okay, I read this wrong. That's why. I have these type definitions backwards. This makes more sense. I was like, these don't make any sense. So is open, the thing must exist for it to be open, right? So if it's in this list, then that file is open. For close, you want to return the list that does no longer contains that key. This makes a lot more sense. Okay. Sorry about that. That was confusing even for me. All right, so the definition of closed file is rather uninteresting. It must ensure a file is already open and then remove it from the indexed state's open set. Close file. Eval is open. Key open is true. Bad arrow. Handle s key linear s linear state. Next, open linear state. I think this is where we use, yep, next. And then we remove the thing. So eval close key open. Oh, so one thing I did. Oh, is this too small, by the way? Can you read this okay? Seems like it might be just a tiny bit too small. I made myself a tiny bit smaller as well. So just to give myself a little bit more real estate. I do want, like, I like having my picture there, but it was taking up too much space. Like, okay. Okay. See, my eyes are really, really bad. So when I pull up other people's streams, I feel like the size is always too small. I mean, always. So I'm kind of paranoid about that. And I usually ask to increase the font size. And if they don't respond, I leave. Simple as that. Okay. So yeah, this is, again, the post conditions are that, you know, you're going to return the set, the open set that no longer contains the key next. Or, well, the key from the handle, sorry. The preconditions can be whatever they are. It doesn't matter what the preconditions are, as long as the key exists in the post conditions of the previous linear state. Or linear action. I'm not sure what the right term is. That's a good point. That's a very good point. Yeah, I'm in 1080p, unscaled. So, but that's like what my computer can handle. If I went higher than that, I would start dropping frames. So I don't do that. And also, you know, my screen itself isn't 4K or anything. So, okay. Actually, my monitors suck really bad. Yeah. Especially this monitor really sucks. I'd like to get it replaced, and I'd also like it to be up there. I think it would be nicer, but anyway, it'll happen eventually. I need more room over here. There's no room on my desk. Okay, enough of that. Next, since we increment next in OpenFile, should we decrement it here? The answer is no. Next is used solely to generate a unique natural number for newly opened handles. If it were decremented as handles were closed, it would be pretty trivial to get two handles with the same key. The type system would get confused pretty quick if such a thing were to occur. So this next thing is only used for opening? I guess I don't fully understand that. Oh, I see, I see it. Okay, I get it. The point is that you want to always be, this should be atomically incrementing. It's like a key in a database or something. It needs to always increase. Yeah, like For whatever reason at my job, somebody recently bought a ultra wide monitor that was only 1080p. It was the worst experience I've ever had. This one's actually fine. It looked so awful. I have no idea why they bought it. Definitely don't do that. Okay. We're now in a position to write a safe version of unsafe run linear. It's safe to run a linear if its final state has no open files. Assuming it had no open files to begin with, we start the next ID counter at 0 and can rely on the ST trick to prevent these handles from leaking out. Okay. So we can run first run linear. Yeah, so basically it's a way, so think of it as a way to link these two things together in the type system. So these two things have to be different. Different? I think so, because we're not using a for all here. So I forget exactly what it does as well. I'm probably not the right person to discuss it. And in fact, the last time when they mentioned the ST trick, I was like, I should read up on that again. So we can look it up in the book again. I can probably find it pretty quick. Let me finish this code and we'll try and use it, and then we'll check that out. Because I would like to remember. It's something to do with like linking between these two types to either enable something or prevent something. Like it's something like that. Yeah. Yes. I think that's how you end up interpreting it. But there's probably a better, like, not better. There might be a more straightforward example that we could just quickly show up on the screen to help us understand this. Oh, it might be right here actually. Let me put these on a different line. Maybe it will make more sense here. 0. So that's our starting state. And our end state must be some number greater than 0 and an empty list. Something? I'm not sure exactly what that A is again. It's a handle, I believe. Yeah, it's got to be a handle, I guess. No, it doesn't have to be a handle. It only has to be some action in the IO monad. Yeah, this is pretty tricky stuff sometimes. I don't know exactly. Like, this is some sort of file IO. But the key point here is that the initial state of this should be an open set, which is empty, and the final state should be an open set that's empty. And you have to do something, right? This can't be 0. So that's the point. Okay, so we're going to try and use this now. Hopefully. So we can just save z stack REPL. We want to be in main, so we'll stay in main. And we can do @c Why would you read @c password? That seems like a poor choice to we'll read oh, password is fine. We can read groups instead, it doesn't matter. I don't think I'm going to show anything on the screen, so it means something has to be done, I think. You wouldn't be able to run linear on nothing, I think. I suppose we can try it. I'm not exactly sure how we try it, but give me a second. So we'll look at Etsy groups instead of Etsy password. I don't think I'm going to read anything or show anything on the file. And also there's nothing in password that would be a problem. But anyway. So now we can look at the type of run linear Etsy password sequenced with close file. Oh, I'm missing stuff. Okay, there we go. Sorry. Yeah, I think it means you have to do something, although I'm a little confused now because I thought that somehow this was going to be embedded into, well, I guess it is embedded in, right? But I was sort of expecting, oh, again, this is one of those things, right? This is describing the action of opening a file, right? It's not doing that. This is actually opening the file by running the monad. Okay, right. Again, you have to separate sort of descriptions from the runtime. I always forget that. And if we did the same thing, we could say run linear Etsy password. Oh, you're right. Good point. Technically, I'm not doing anything. Unless I was to try and pull something out of it. Okay, so this is trying to run linear with only opening the file. We're not closing the file. And you'll see, basically, could it match a list of something? Hey, Jappy. How are you? It's trying to find a list of something, and it's getting a list of nothing. Wait. Oh, no. The result of run linear Etsy password has a open sum with something in it, but it needs to have nothing in it. Yep, here's the expected type. So if we did two things, I guess we could sequence Etsy password with Etsy password, and this should be 2, right? Damn it. I want to test stuff out now. Oh, well, that's not going to work. What if we find close file and sequence? Well, anyway, here's the one. It doesn't print. It doesn't print this, which is what I was hoping for. I wanted to see if there was going to be a 2 there. But you can see that it's like, it doesn't have the 0 anymore. It's a 1. So that's kind of interesting. That's kind of weird. Okay. We could also try and close the file more than once, which I assume is just close file, probably. Oh, no. This makes sense. Right, so we're gonna try and close this file twice. Oh, okay, this is the arrow. Or the error. Again, this one is like awful. But again, we learned how to fix these type errors, so you could easily augment these functions to give you better type errors. So that's kind of nice. What's this one trying to do? Okay, so then the last thing we're going to try to do is leak our file handle. So we're going to open a file, we're going to close it, and then we're going to try and leak it. This is where the ST trick is coming in handy, by the way. So like, I don't want my file handle to ever leak from, I guess, this context here, this linear context. So this should fail to compile as well. And it's gonna be, so yeah, the point is they're always different, so the types don't work. So it's, I forget exactly how you wrote it. Yeah, because they're both existential, you know, the type systems never match. That's wild. Again, we can also clean this up, so very cool. So index monads are a great solution to enforcing invariance on the ordering of monadic actions. Because they're slightly hampered by their syntactic limitations, and as such probably shouldn't be the first tool you reach for. Yeah, it is. It's very cool. I'm a big fan of it. I do remember what's reflex. I actually don't know what that is. So Jappy, just for reference, there is tricks in Haskell to making these errors look a lot nicer, and we covered them in either chapter 12 or 13. So like, yes, this is awful, but I could make it a lot better. So like, if this was a real production library, we can clean these errors up quite a bit. Okay, so that's index monads, so that's cool. And also I should, grenade, I don't know what these packages are. Is that a Haskell package? Deep learning. Actually, I have heard of this. I've not heard of reflex yet. Have you tried it sounds like you're interested in deep learning. Have you tried HaskTorch yet? Front end tech. Maybe they don't know how to do it. They got to read this book. They probably do. I've been meaning to look into HaskTorch, Jappy. I'm pretty interested in doing deep learning myself. I was doing it all day and it was miserable, but I'm learning. Yeah, so HaskTorch is just like a Haskell front end to PyTorch, or well, Torch. It's so hard. Like today I was trying to build custom neural nets, and like I thought that I was doing the right thing, but then it wasn't. So now I'm blaming my data, And I'm afraid, like, I don't know if it's my data or my network, and like I just have no idea how to figure it out. Yeah, I think this contains something about the I did see documentation for this somewhere. I just don't remember where it is. I thought I did. Anyway, TensorFlow has a official Haskell API. I didn't know that. Interesting. Oh boy. Yeah, I'm not gonna look at this now. This could be uh, a deep dark hole to go down. Well, that's cool. I'm definitely interested in doing data science tasks in Haskell, so I'm hopeful that I can start doing that soon. It's just like I've relied so long on pandas that I'm very fluent in pandas, and like I don't want to spend all this time becoming fluent in Haskell when I know something, I know something that works already. But there are benefits to be had for using Haskell as well, so. Okay, anyway, we're actually done with chapter 14, so... Yeah, you mentioned that before, Lumi. I thought that was kind of interesting. All right, so guess what, folks? We are actually on the last chapter of this book. Insane. Closure. Okay, I've not messed with Closure. And Jappy, I'm a data science noob too. I just pretty familiar with pandas at this point from doing sort of data wrangling mostly. Okay, so Stack New, chapter 15. And this is the last chapter of the book. How insane is that? I feel like we learned so much, and I think it's going to take us a while to really absorb all of this, but I'm happy that we have it in our heads now. Okay, we've updated our title. We need to fix the following files. Man, how crazy. Dependent types. I almost just wrote readme. Done. Okay. So, yeah, let's talk about dependent types. I know that I'm very interested in dependent types because, well, actually, as I don't remember, I think it was Jappy mentioned, Grenade has dependent typed neural nets, which sounds amazing because you can't screw them up. You can't screw up the dimensionality anyway at compile time, which is kind of what I am really excited about. And there's other situations like making sure that your functions get non-empty lists without having to have a special type for non-empty lists and these sorts of things. So I'm pretty excited about using these at some point, and we'll see how that goes. I have no idea what we're gonna need yet, so let's do a little reading. Um, Dependent types are types which depend on the result of runtime values. This is an odd thing. In Haskell, traditionally terms and types on different sides of the phase barrier. Terms exist only at runtime and types only at compile time. Oh, I guess that's a good point. The dependent types have to be at runtime, right? So you have to, what's the right term for that? You have to reify the types? Or wait, no, you only need the values, I guess. Anyway, I don't know the terminology. Hopefully it will become more clear. Proponents of dynamic typing are likely less fazed by the idea of dependent types. Their typing mechanisms, if they have any at all, must exist at runtime. But as we will see, we do not need to give up type safety in order to work with dependent types. The field of dependent types is fast growing, and any attempt to describe it definitively is doomed to fail. Professor and GHC contributor Richard Eisenberg is actively working on bringing first-class dependent types to Haskell, though his projections estimate it not to be available for a few years. In the meantime, we have no recourse but to abuse language features in order to gain an approximation of dependent types, content with the knowledge that content with the knowledge that the process will only get easier as time goes on. While the techniques in this section will likely be deprecated sooner than later, the ideas will carry on. Also, a good combination of ideas already presented in this book. Motivated reader can use this section as a test to their understanding of many disparate pieces of the type system, including rank n types, GADTs, type families, data kinds, among others. So I think it's available singletons. I think I've heard of that before, but maybe that was like, that's recent. I feel like I remember seeing something about this singletons. It's a package or something, right? And anyway, or maybe it's another trick. Okay. Oh, it says dependent types in Haskell can be approximated via singletons. Yeah. Literally the next chapter I was going to read. Or, sorry, next sentence. Very funny. Okay. Consider the unit type whose only inhabitant is the unit value. This type has an interesting property. If you know a value's type is unit, you know what the value must be. The type unit is a singleton because it only has a single term. Furthermore, because of this one-to-one representation, we can think about the unit type as being able to cross the term type divide at will. Singleton types are just this idea taken to the extreme. For every inhabitant of a type, we create a singleton type capable of bridging the term type divide. The singleton allows us to move between terms to types and vice versa. As a result, we are capable of moving types to terms, using them in regular term level Haskell computations, and then lifting them back into types. Notice the data kinds already give us type level representation of terms. Recall that prime true or tick true is the promoted data constructor of true. Okay, so let's implement this thing instead of talking. I learned from writing, not talking. But sometimes sometimes you have to talk. Type applications, type families, and finally type families dependencies. We have not used type family dependencies yet. That's the new one, I guess. Okay. Necessary imports. Import control monad trans writer. That's fun. We're going to use writer. Import data constraint I have no idea what this is. Data, foldable. This one. Line 14, Lumi. I assume that's the one that you're discussing. Or is it the type family dependencies thing? It's either that or like the combination or something. Okay. I will assume that the delay is for constraint dict. Okay, now we need to get these things, so constraint. Spelled that right. This one needs transformers. Google. It's in a package called constraints. Okay. Whoops, wrong way. 24G constraints stack build. Wonderful. That. Okay. So to wet our whistles, let's first look at a simple, speaking of that. I'm so funny. Let's first look at a simple implementation of singletons. We begin with the singletons themselves. Data s bool b bool. So gdt s true s bool true. False. False. This is a dependently typed matrix. Oh, yeah, I've seen H matrix before. Oh, that's fun. I forget sometimes that you can do Unicode in Haskell. I don't like writing it, so. But yeah, okay, that's awesome. Although, I'd prefer if this was an I. Well, I guess it's like a complex number, so they must use I to represent the imaginary part somewhere. Now I want to look for it. Yeah. I'm surprised there's no imaginary component. Oh, it's just a, I see. Okay, it's just a alias, that's why. Anyway. Okay. Let's go back to where, oh. Nope, nope, nope. Button. Okay. All right, the data constructors as true and as false act as our bridge between the term and type levels. Both are terms, but are the sole inhabitants of their types. We thus have isomorphisms. S true is congruent to prime true, tick true, whatever you want to call it. It's the promoted data kind, this one. And S false is I'm not sure. I've always pronounced that one congruent. It's the sim above equals. I mean, it's supposed to be like equivalent because they're isomorphism. Anyway, the next step is to find an isomorphism between bool and S bool B. This is easy in one direction from S bool. And then we need to go to the converse is trickier because S bool true is a different type than S bool false. We are unable to directly write the other side of the isomorphism. Instead, we introduce an existential wrapper, some S bool, and an eliminator. Kind of new. Some S bool. Where? Some S bool. Let's put this. Some right. This looked really strange at first, but right, it needs to be able to represent both true and false at the type level, excuse me. It needs to represent both kinds at the type level, right? I think that's the right way to say it. Because this has to be, this B here can be either prime true or prime false. So it's the, yeah, I think that's right. Or I'm saying it right anyway. It's always hard to say. It's a negative for all. A negative. I don't know what you mean by negative. Anyway, we'll keep going. And then we can just write 2s bool to some s bool like unfortunately that doesn't help. Like before the arrow. I've just not heard the term negative for all before. I think that's why I'm oh, I see. Okay. Yes, I understand what that means. Uh now that you now that Lumi basically just said contravariant covariant. um but it is, isn't it in both positions? Isn't it both positive and negative? Because it's on the right and the left. Oh, but I guess the whole thing is on the right. This is on the left. Yeah, just B, exactly. Okay. Yeah, yeah. What does that get me? I'm just trying to make sure I see where you're going, because I want to understand. What does knowing that B is contravariant? No. Negative is covariant, right? Positive is contravariant? I forget the trick now. I guess that would make sense. What does knowing that it's contravariant help me achieve? I suppose. That's the part I'm confused about. Because I think B is just representing a either tick true or tick false kinds. And that way at runtime we can determine, oh, okay, you're just saying it's interesting, more or less. Okay. I see what you're saying, I think. Yeah, so it's just that the caller of this function decides at runtime what the value of B is for. Or what, I'm sorry, what the kind of B is. I think I'm saying that right. So the caller in this case will be, actually I don't know who the caller is. The caller is just someone. Well, I'm going to use it in a second, so hopefully it will help. Oh, S. Okay. So, yeah. So I didn't need to close that. I need to say that to myself out loud often. So anyway, it says, it makes intuitive sense that to_sbool would need to return an existential type, as there is no guarantee its arguments are known at compile time. Perhaps the bool being singletonized came from the user or across the network. We can convince ourselves that from sbool and to_sbool behave sanely. So with some sbool to_sbool true, from sbool true. What? Oh, I'm dumb. Sorry. There's no, usually he does these with arrows and I'm just reading incorrectly. So my apologies. It makes sense now that I'm thinking about it. Sometimes I just type and that's not always the best idea. Right, so I guess this implies that the runtime determines that this B is true, therefore we return true from this. And we can do the same thing with false, and it behaves the way we expect it to. So that's how we link the term and type level, I guess. So as an example of the usefulness of singletons, we will build a monad stack which can conditionally log messages. These messages will only be for debugging and thus should be disabled for production builds. While one approach to this problem is to simply branch at runtime depending on whether logging is enabled, this carries with it a performance impact. Instead, we can conditionally choose Instead, we can conditionally choose our monad stack depending on a runtime value. We begin with a type class indexed over bool. It has an associated type family to select the correct monad stack, as well as a few methods for working with the stack. So class monad logging monad B. Monad logging B bool. Oops. Or use cpragmas. Sure, that would work. It would be, I suppose, awful. Is it awful? I mean, you're doing not like this, so I assume that means it was really hard or annoying or something. Not Haskell-y. I don't know what the right term is. Yeah, that's true. Yeah, you get the type checking at compile time either way. I guess that's a good point. You just have to make sure your pragmas are in the right place. Okay, anyway. Type logging monad B equals R type. Here, let me sub. Yeah, I mean, it's kind of like that might be one of these if it works situation. At least you're still checked by the compiler, right? It could be worse. Ugh. Yeah, that's true as well. No worries. See you later, Jappy. Sleep well. I needed to take a drink. That's what I need to do. Thanks for stopping by. Yeah, I mean, this is semantically already pretty daunting. Sorry, just a second. Okay, nothing important. All right, so this is the style that was used, but this was tabbed out one more. Not sure I like this style, but we'll just leave it as is. I mean, they're doing this to, you know, save space essentially. Lumi just resubscribed. 3 months. Insanity. You're a crazy person, and I appreciate you. Thank you very much. Does that, I'm not sure if that actually makes 4 subscribers. I'm still very confused about the way the subscriber goal thing works, but it'll recompute correctly next time. So we'll count it as a +1. I'll take it, even though you're resubscribed. So I'm not sure what that means. I mean, I know what resubscribed means, but I don't know why it goes up, the counter. Okay, anyway, so oh, so this is just a type family. One thing is kind of funny. They put a 1 and a 2, but don't say anything about 1. It's kind of funny. Only the 2. The only thing that's important here is that this R means R implies B, right? If it knows logging monad B, it can infer B. Okay, anyway, that's a lot of syntax right there. A little hard to read. So we can write the instances for this. False. Logging monad. False equals IO. Nice. Id. So this is the do nothing case. So if your logging is off, basically just return nothing. Or, well, return do nothing effects. This is kind of interesting. Run logging equals id. Run logging equals id. How? Oh. This is probably just because I've not played with this logging monad. Because we didn't no, we just defined this. Is this why? B and A ignores B. Uh, uh, I'm still lost. Need to think. So this thing is my understanding this correctly as it's partially applied. R is partially applied. Or I'm sorry, it's point free. As in No, yes, I think. Is that right? So this R is just IO, and it's taking an A as its argument. And this is an A. Well, this is an A. Yeah, this is a little tricky to me, but I think I get it, but probably not. Maybe it'll make more sense when we get to like the defining custom monads parts. But anyway, that part makes sense. Like this is partially applied. I keep saying that. This is point free. It should take an argument. That argument would just be an IOA essentially because we've defined this, and therefore it just returns IOA. Sure. I'm gonna keep going. Fun. Oh, okay. It just needs me to define run logging. I hate that so much. I don't know how to fix that. Okay. So is this, just for my reference, is this the same as saying the following? Yep. Right, because we're getting a string, so that's there. And let's see what the type of this is. List of string to writer t list of string IO unit. Okay, cool. Actually, I think this helps quite a bit. Like, this is almost more confusing to me. Maybe. It's really cool. I can't wait until monad transformers make sense to me. Like, I sort of understand now the functions involved and the machinery, but I really would like to understand this stuff like little bit better. So I'm, you know, we should be able to finish this book, maybe even tonight. I don't know how much is actually here. It's mentally pretty challenging, but then we'll start Book of Monads and get into the custom monads chapters, and I think that's going to really solidify the monad transformer stuff for me. And if that doesn't, we'll start just writing monad transformers for, I don't know, all kinds of stuff, I guess. Maybe we'll write more of this kind of stuff as well. Okay. Now, what's going on here? So what is, so W is gotta be, sure. Okay, list a string, that's what I thought. And what's this A? It's gotta be, it's just gotta be something. It's the A that comes from running this monad. Because we have like a writer T, string IO, and some action A. So that's what A is. So it should just be A. Wonderful. Okay. So what's for do? For takes a list of string and a string to IO unit and produces IO. So that's the put strlen. Okay. So we can just close that. Cool. So this makes sense. This just gives us back a writer T string IO A, and we perform our effect by writing output to the console in this case. I suppose it would probably make more sense if somehow we prefaced it with like debug or something like that. But you know, that's probably not that important. Like, you know, the fact that we're writing it at all is good. Yep. Yeah, I'm good there. That part makes sense. This 4 is new. Well, maybe it's not new, but it probably is. Yeah. Wait. I thought the result of this final line was going to be this whole thing. It's not. It's just IOA. Right, because we're running the writer T. Right. No, I get it. Yep. That pure is actually, well, we can just look at it. It should be A to IOA. Yep. Thank you. Good point. Very good point. Nice. Nice. Okay, let's keep going. So, let's write a main function. That does this, I guess. So we're gonna make some arbitrary program. We should call this function business logic, right? Oh. Every time. I just have to type faster. The thing is that GHC is too fast for me. It just happens automatically. Like, if we just have do, and then I hit enter, it selects this first one. So it's kind of like, so if I press up, enter, it would be fine. Yeah. Maybe, but I kind of like it this way, generally speaking. You know, it's only with the do that it's a problem. Like what I need to do is just remember that in most cases I need to, or in some cases I need to press up and enter instead of enter. I don't know. Maybe there's a better way to do it. We can look at my vimrc at the end if we finish. I'd like to get through this content because I really want to start working on Book of Monads next week. I think this is the. I think that this is the logging message. I'm not 100% sure exactly here. So like up enter, but then I have to press it twice, so it's like kind of a pain in the butt. So we're gonna give it a function or a boolean. Yeah, see, like that one's not what you want either, so maybe it makes more sense to like not jump directly into the selections and force ourselves to tab through them. We can see if we can fix that. We need 2s bool $, given anything. Okay, so we need scope type variables and we need type applications. Oops. No instance for monad logging B arising from the use of. Maybe this is just like an extension I'm missing. Or maybe I have a typo. Oh. Logging B, bad arrow, logging monad unit. Oh my god. I hate when I do this. I see an error and then I start reading the error message, but it's explained in the book. My bad. Hang on. Okay. This function reads a bool from standard in and lists it into a singleton at 1. The resulting existential type B is bound at 2 and type applied at... Oh, I should explain what 2 is. Bound at 2 and type applied at 3. The problem is that type classes are implemented in GHC as implicitly passed variables. By 3, which is this line here, GHC doesn't know the type of B and thus can't find the appropriate monad logging dictionary, even though monad logging is total and theoretically GHC should be able to determine it. We can help GHC along by writing a function that can deliver dictionaries for any constraint that is total over bool. So do I define that here or do I define that in lib? I'm not sure. We can try it. We'll start here because I'm here. Actually, we should define it in lib because we're probably done with this. In source And we'll go down here and we'll type the following. Dict C. No idea what C is. Guess that's the point. Okay. Dict works by requiring some bool to constraint to be satisfied for both true and false. Some constraint satisfied for true and false. Okay. It then takes a singleton and uses that to deliver the appropriate dict by branching at 3. The fact that both branches simply return dict might be confusing, but remember that GHC infers different types for them due to the type equality implicit in the GADT match. Dict can be invoked with a bool to constraint type application to select the desired constraint. Finally, we can write a working main which acquires the correct type class dictionary using the singleton it lifted. We write case dict at monad logging SB of. And then I need to import this. Gee. What is this SB? It's no longer existential. Not existential, that's not the right term. It's no longer anything. We have to explicitly use it this time. Okay. Sure. So stack run. True. Okay. Logging robot. Achieved. False. We get nothing. Pretty cool. Pretty cool. Here we have provided an isomorphism bool to S bool A and from S bool A to bool. Because isomorphisms are transitive, this means we have the desired correspondence between terms and types as witnessed by bool to A, which has type bool. Okay. Interesting. That's pretty wild. Sorry. I had to go to the eye doctor today, and they always mess with my eyes, and so my eyes are very, very tired right now. I need to take like a minute here. Yeah, so we're going to be doing, apparently there's a generalized way to do this, so we're going to do that next. But I think you're right. So we are going to write some sort of generic singleton machinery, I think. So let's put that in sing.haskell, and it's probably going to have a majority of the information from here. So we'll just copy it over. And we're probably going to need these things, I would guess. This is going to be called sing. And we're going to need a million more things. We need where's my cursor? Flexible instances, data kinds, GDTs, constraint kinds. It's not on here. Get rid of that. GDTs, kind signatures, polykinds, Rankin types, scope type variables, type families, type family dependencies. Apparently we don't need type applications. Type, in type. I don't remember what that one means exactly. Type operators and undecidable instances. So anytime we add undecidable instances, that usually means we're going to be doing something a little wild, right? We don't need this. We don't need this. Import data typable. Import data void. Import unsafe dot coerce. Safe. Coerce. Type in type is deprecated and does nothing. Okay. Well, hopefully it does something. I guess we're gonna find out, right? I mean, some of these, I mean, it says here that like these aren't even necessary, right? Like technically we can remove these and that wouldn't do anything. I mean, we don't see any type applications. And actually there's no type families in here either, right? Although this is something. Yeah, yeah. But that's okay. We'll just leave it like this for now. Okay. So it says, while the S-bool approach works well enough for lifting bools, it's not immediately evident how to generalize the pattern to be ergonomic when working with many different types. We begin with a polykinded open data family, which is responsible for indexing the equivalents of S-bool. Data family sing a k. Okay, so that's the eliminator, and then with some sing k, oops, or all a k sing A to R to R. Okay, and then our function to bring things down. Okay. However, it is more ergonomic. I don't know why it's however. It's more ergonomic to package together toSing and FromSing into a type class rather than be independent functions. Phone's blowing up, folks. Okay, where type demote K equals R, where R is dependent on K. What's the right terminology here? Where R implies K, I think is the way you say it. Do 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 do. I think it implies toSing. Why is it called demote? Where's this demote thing come from? I guess it's like demote from the type level. But not sure. Not sure why it's called demote, but anyway. Maybe it'll make more sense here in a little bit. Let's ZT that. So it says, notice at 2, the type variable K is used both as a type and as a kind. This requires the type-in-type language extension, which removes the distinction between types and kinds. Additionally, it makes the type, like capital type, an inhabitant of type, the constraint type, which is now the same thing as type itself. Mathematician readers will likely fear the unsoundities resulting from this change, but Richard Eisenberg, the author of this feature, assures us these paradoxes are not observable in Haskell. The associated type family demote K, okay, nice, is an implementation detail. It is almost always equal to K, except in cases where GHC already provides a type literal for nat and symbol. For example, nat and symbol. A type family dependency is added to demote, allowing GHC to infer K from demote K. Yep. Instances of sing and sing kind are trivially provided for bool. I don't remember discussing these data instance things. I think this is an analogy to this being reification of types at runtime, such that pattern matching can be done. So either promote it or demote it. I thought a GADT was just data, like this one. I thought this was a GADT. Oh, this is the instantiation of the GADT, yes? Is that the right way to say that? Yeah. I'm not sure either. Hang on. It says instances of sing. Oh, that's okay. This is a data family. Sorry. So that's an instance of a open data family. There's, I guess, open type families and open data families. So this is an open data family. That's the instance of the open data family, which explains why you can have s true and s false, right? If we're defining the instance of this, it must define a function that's called sumSing. So yeah, this is, let's put that here. That makes more sense. Okay, and then oh, I wrote sing king. Okay, there we go. Type demote bool equals bool. So yeah, almost always equal to the same thing. To sing true equals sum sing s true. To sing false equals sum sing false. From sing s true, oops, s true equals true. All right, so oops. Thank you, compiler. So by using type in type, we basically are making this instance a lot easier to write. There's no machinery, there's no theatrics needed to make this work. It's just like trivial to convert between them, I guess. I think that's the easiest way to say that. So then we can do okay. Okay. Because singletons are the unique inhabitant of their types, at the term level, they are isomorphic with a unit. Therefore, we expect to be able to get this unique inhabitant in the same way we always conjure a unit out of thin air. What? I don't understand the point of this. Why is this called sing I? I don't understand what it's for. I'm not entirely sure what the point of this sing I piece is. Anyway. Oh, you know what? I just realized I think that that's the right REPL that we want. I'll write this in here, but I'm not 100% sure what it's for. What is this for? Maybe we need it later. Oh, we do need it later. Wait, do we? I don't know what this is for. Is this just the isomorphism? I thought this was, I mean, this is the isomorphism. What is this? I don't understand this purpose. Sing I. Okay. The reverse of sing. Okay. B to. So it's, oh, okay. So it's the okay. It's the inverse of these instances, essentially. Okay. I'm not sure what it's for, but mainly because it wasn't motivated. So it's hard to tell. So it says the sing function can be used with type applications in order to retrieve the desired singleton. Okay, fine. Let's do something more interesting. Oh, yeah, that's kind of like a pure. Oh, that's what it is. It's like pure, right? I guess it's kind of like pure. Not really, but kind of. And either way, it would be helpful if it was just more obvious at why I need it. That's the only, or would need it, when I would need it, something like that. Sing kind, maybe, K. Type. Demote, maybe. To sing just a equals this is not what I was expecting, but okay. With to do, that's fine. To sing a yeah, so I'm not sure exactly what it's for. I guess it could go. I don't know where it goes. You need it for some type level machinery, but not for this, I guess. So let's see here. How does this nonsense work? Okay, so with something takes a an F and applies S to it. So something should say some singleton. I don't like saying something for some reason. Takes a singleton and returns some singleton. So S just does that. And this essentially rips out the A piece so that we can put it in a just. Okay, interesting. That's not behind my head either, right? Nice. Okay, so smaller me is working out. But just some okay. So, besides some relatively tricky wrapping of existentials, there is nothing new or interesting in this code. The given data constructor is built out of other pieces of data. Its singletons are built out of the analogous singletons. Its data kinds out of the analogous promoted data constructors. To get a feel for this transformation, we can also build singletons for lists. Oy. What's up, Oren? We are getting our mind blown as usual. How was your day? We are actually almost done. I'm gonna be here for another hour, or when I finish this chapter, whatever comes first. There's actually quite a bit of content left, so I don't think I'll finish. I don't think I'll finish the chapter tonight. So there's another hour of streaming left. Installing things around the house. Anything interesting or just kind of random stuff? Well, you don't have to share if you don't want, obviously. Weird. Oh, I'm missing an arrow. And a constructor. Weird. Okay. That's not that scary, though. This is kind of scary. Excuse me. Currents. Currents in TV. Easy, pretty relatively easy stuff, more or less. Yeah, I need to really play with Nyx as well, so that's gonna come eventually. I don't know when, but it's going to come eventually. I'd really like to start some projects on the stream. Um, we haven't done that. We've only been learning. Yeah, like the ideas are pretty great, but it's relatively hard to use. Is that why the hate part thing? My understanding is it's really hard to learn right now. Like there's just not a lot of content for learning it. Maybe that's not where you're going with that, but just love. Okay. Fair enough. Aren't those things coming though? I was under the impression that people were pretty excited about the future of Nyx. Because it's sort of taking off, right? Okay, this is going to be a little tricky, I think. So we got 2 sing H, and then the sh. Keep doing that. 2 sing T, tail, some sing scones, SHST. Oh, where? Yeah, I was actually surprised when I saw how old it was, because I only just recently heard about it. S-nil, D-list. Oh, for sure, for sure. Give me just 1 second to finish this code, and then I will do that. Okay, so let's put that aside for a second. So first things first. Oh, not in here, in here. So we finished our index monad solution. So basically what we did in here is define, I don't know if you were here last week on Tuesday, but we defined this index monad, which basically describes the order in which a monad is required to run. So each of these linear state things has a like a beginning sets of requirements. That's okay. I can explain it. Let's go up here a little bit. So there's basically two of these states. Okay, so there's an like a precondition and a postcondition. I'm trying to look for the right terms, and I'm just making sure I'm on the right page. All right, so we have this index monad thing in the IO that has some preconditions and some postconditions. So what we're gonna do is write a open file and close file implementation such that I can only ever open a file and close a file once. I can never open a file and leave it open, and I can never close a file twice, and I can never open a file twice. Okay, so that's kind of the idea. And by using this index monad, you can force those things to happen. Okay, so our open file looks like this. So given some precondition and some postcondition, doesn't matter what they are. To open a file, what we need to do is increment our next precondition so that we have this new postcondition. And we also need to add the next to our open sum is what this ends up being. So this is just a list of numbers, and this is just a number. Okay, so the number always goes up, and this can get bigger and decrease depending on the open. Yes, exactly. Actually, by doing this, it's embedded in the type system already. So yes, and that's the point. You're gonna see that when we try and compile certain expressions, I'll show you them, that they won't work, and you'll see why. Or, well, the errors will make zero sense, more or less. The first one does, but the rest of them are just archaic. But that's okay. We can think about that. So yeah, that's the rule. When you open a file, this thing gets incremented, and we add some value to this open sum. Okay. Then we can describe basically two type families. One of which is like, is this file open? So if we go look for a key in that open sum and it exists, right? It is a just, then the key exists in the open sum. So the file is open. To close a file, we basically are removing that key from TS. So you can say this is like filter not dot equals key. That's the idea. Okay. So close file looks like this. Given some preconditions and postconditions where the key exists in the open conditions, okay, right? They have to be in this open sum at the beginning, otherwise we can't close it. That's the point. That's the link you need. And then all we do is to compute the new I'm losing my terminology. To compute the new open sum, we basically just remove the type from that open sum. Okay, so you're gonna have this like ever increasing number, and then this open product which gets smaller, and you can open and close files. Okay, finally, you have this run linear function, which basically allows you to open and close a file and not do any of the sort of nasty things. So the nasty things are opening a file and not closing it, opening a file twice, closing a file twice, trying to pull out the file handle from the trying to pull out the file handle from opening outside of this context, and that's handled by this S thing, which is called the ST trick. So anyway, let's see what this looks like in practice, and hopefully it will make sense. So if I remember correctly, we can do type. We need to define something. So we're gonna say our, I don't know, Etsy, what did we use before? I think it was group. So Etsy group equals open file slash Etsy groups read mode, I think is what it is. All right, and then if we want to look at the type of run linear Etsy group bind, oops, the other way, close file. Okay, so right, this is opening the file once and closing the file once. This type checks. All right, so now let's try something like closing the file twice. So if we give this a function, close file f, doesn't compile. If we try to, how did I do it before? If we try to open a file twice, it doesn't type check. If we try to leak, how do we do it before? I think it was like close file. No, it was just, I think it was just pure F, right? I think that's how we did it before. So if we like try and return the handle, we can't do it. So anyway, all of these sort of nasty things one could do with handles goes away because we're enforcing that this be true. Sorry, yeah, this be true. You can only open it and close it. And you have to close it. Is that interesting? I went through it kind of quickly, so you might need to go like poke around the code a little bit more, but it's kind of neat. Yeah, you could see how it'd be useful. I think that's a good example of it being useful. Okay, so that's that. Now, in chapter 15, we are, we're basically trying to embed dependent types into Haskell. So you do that via this thing called singletons, and I'm not, this part is a little harder for me right now. Like it's kind of over my head a tiny bit, but we'll start here. It's kind of the easiest way. So to do that, you define a GADT, which defines some constructors. So S true and S false for true and false, right? And this basically just maps your kinds into, you know, true and false. And you can basically define an isomorphism between S bool B and bool just by doing this. Now to do it the other way is tricky. So you have this thing that they're calling an eliminator, and it's basically so that you can take a bool and return either S true or S false, right? That's the point. These are different kinds, so you need to wrap them in a little trick. So anyway, with some S bool gives you the S bool and then a way to turn it into a bool. And that's basically what this is doing. So we just are taking an S where B gets determined by the caller of the function to return some R, and then we can define our to S bool. Then, using this machinery, what we do is define... Wait, did we use that machinery? We didn't use sbool at all, did we? No, we didn't. What was the point of... I mean, I know what the point of this was, but how did we get from... I think we changed topics, is that right? Let me look. Oh, okay, so this is an example of how you would... Like, this was just like, look, this is how you use singletons. And then this is like a real example of using singletons. So if you can define like a logging system that is completely ignored at runtime by a dependent type. So that dependent type is some Boolean, and if that Boolean is false, essentially we kind of just ignore everything. And if that's true, then we like write something to the output. So that's what this piece is doing. So I can show you that in action. We can just say stack REPL, and then our main function will wait and take a true or false, basically. So if we give it true, it converts it to the Boolean true and then runs some log function. And if we give it false, it doesn't do anything. And I'll show you the main function. So you see it. It's basically like this. So give me this thing, and then either run the logging or don't. And this dictionary thing is a implementation detail for GHC because it can't determine the types correctly at compile time. I think that's the right way to say that. It can't determine this type, so you have to like provide some machinery to make that happen. So that's the usefulness of dependent types. And now, what are we doing now? Interesting to think of type classes as just being dictionaries. It's a good point. And now what we're doing is using a generic version of that that some bool trick to encode like various different type classes. So you can like, for example, you can encode, where'd it go? True and false like this. So instead of all of that junk, now you just have this. You can also encode maybe types. You can encode lists. So you can use this singleton trick to do all kinds of stuff, apparently. So that's what we've been doing. It's been pretty wild. I'm pretty happy with this chapter, though. It's pretty fun. It definitely got me thinking. Okay. Okay, now we're gonna do, so there's an exercise here, so we'll do the exercise. Finally, an exercise. So that one's trivial, so it's just instance sing I empty list sing equals s nothing. No, s nil, not nothing. What are the pros and cons of doing this same thing in runtime versus compile time? Well, Okay, so at the runtime, I think we were sort of talking about this earlier. So at the runtime, oh, sorry. Let me say this the other way. If you want to do this at compile time, you have to have branches. And apparently branches can make slow things down in certain cases. So like if you have a monad logging that happens at compile time, you have to create a branch in your code to say, if this static variable is true, go do this thing. If it's false, go do that thing. If you let it happen at runtime, you can have these, you can just have it at runtime. And then the other thing that I think, sorry, who was it brought up? My brain is fried today. It's always fried when I do this. Not Mitch. Jappy brought up is that you can also do this with like pragmas, and that would handle the runtime thing. So you, instead of having branches in your code, you just have pragmas that get compiled out, more or less, or code that gets compiled out or in, depending on some value. I think. Now the pros and cons of that are, I don't have any pros and cons. I just know that those are the two things that are possible. I wish I had more information for you. I just don't. Maybe Lumi hit it. Maybe Lumi does, but I think even Lumi said that the pros and cons are debatable. So, or something along those lines, anyway. Yeah, I mean, that's true. Conditional compilation avoids the branching, so it's along the same lines as dependent types. But you're relying on an outside system that's not the Haskell language. That's okay. You'll have to watch the video though. I don't think I can say that again. Unfortunately. All right, so how's this work? So we need to have a good. Thank you. Each of these need to be, oh gosh. No worries. We will be here for a little while anyway. So we're gonna have no, that I put this in the wrong place. Shoot. That's not what I wanted to do. So It's just supposed to be sconce sing? Oh, sing. Okay, right. So is this supposed to be empty list? Yep. And this is okay. I hope this is right. All right. So anyway, Oren will probably be back and read this. All of this is debatable. Types constrain your thinking, and a lot of times this may lead to overcomplicated solutions. Getting things to be type safe for the sake of it can be hard, and by extension, super fun puzzle. That's kind of why we're doing the book, but it's rarely really all that valuable. That's one of the reasons I, for example, don't use Haskell for my actual work. Yeah, that's kind of the like dynamic. Well, I know that you said you use Clojure, right? So dynamic typing and dynamic runtimes do make your life quite a bit easier at times, depending on what you're doing. All right, well, this is cool. I think this is right. Anyway, I'll check the solution real quick, but I'm pretty sure it's right. 15, 3. It's close to right, but I messed up the... It's really supposed to be the following. So that this is type T. Otherwise, you can only have a list with one thing in it. And by default, the compiler gave you that this was empty. Well, S nil, more or less. Okie dokie. What's next? We have a half hour, so we got plenty of time. So now we are going to use singletons, which is a package, and template Haskell. Okay. So let's start a new... I probably shouldn't call it singleton. I'll call it... so that we can keep this. We need data kinds. Well, let's just copy all of these and delete the ones we don't need. We don't need these. And SIGs is one that's not in here. Kind signatures, polykines. Type families. Undecidable instances. And template Haskell. Okay, so now we're going to use some code that is going to yeah, apparently this is going to write singleton instance for us and promote term level functions, apparently. I will see. Singletons. Stack build. Let's see if we actually need to build anything. Yes, we do. Okay. Building, building, building. Doop doop. Mm-hmm. Mm-hmm. Compiling. Takes a little while. Yeah, we've been doing pretty good with followers recently. We got I forgot to mention these, but the last stream, right as it ended, 2 people followed as well. We got VHGI, which their name is Vic. They messaged me personally to tell me that because their name is purposely unpronounceable, I guess. I just made something up. And Dredsky also followed, so that was pretty awesome. We got Ken Felling today. We're up to what, 106? So slowly working our way to 200, maybe. I mean, we'll see if we ever get there. Hard to say. The stream's been pretty quiet. I think we'll probably get a ton more followers when we do the category theory book. I think that'll be pretty interesting. I'm not sure anyone's done stuff like that before on Twitch, so should be kind of interesting. If you don't know about that, let me put that here. Here we go. So that starts at the end of the month if you want to be involved in it. 3rd Monday this month. And you can get that book for free, so you can hang out with it. User inputs is involved. Gives it less value to try to make it typesafe. Ow. I don't know how I feel about that statement. But I also have a lot less experience than you guys, so. We'll see what Lumi says. Man, this is a big package. I guess it's not that surprising. It's got to write singleton instance for everything. Do. Hello, random viewer. We are currently compiling singletons, and then we are going to try and use singletons. And that's probably going to get us to the end of the stream, which is about a half hour. So if you want to hang out, feel free to hang out. Don't really know what we're going to be doing, so we'll see. We're almost done with this though. And they promptly left. Fun. I wonder if like the actual viewer count goes up way later than that person actually starts. So if I don't explain randomly what's going on, then those people just leave because they're just like, oh, that person's just compiling stuff. Yeah, contracts. That's how I think of it. So like, especially in the case where, or the most obvious solution for me is like, I want to make sure that my function gets, I don't know, a Hermitian matrix, something like that. Or I want to make sure I get this function gets a non-empty list, right? Without having to deal with the the theatrics of, I've said theatrics twice today, without having to deal with the theatrics of using the non-empty list type, right? It's kind of nice to just be able to write like your normal list stuff and make sure that the function takes a non-empty list at runtime. So I think dependent types seem really cool. I can think of a few solutions like in my head where I think it's important. Which is part of the reason why I want to mess with Idris. Sort of waiting for, I guess, Idris 2 to be ready. Is that the right term? I think ready is probably a fine term. I could see it being useful for library writers. Man, this takes forever. I guess it's compiling an entire prelude, so it's not that surprising. So essentially I shouldn't update my version of GHC anytime soon so that this is pre-compiled. Although I don't think there's a new version of HIE, so I won't update until there's a new supported version of HIE. I can't believe we're almost done with this book. It's insane. Who would have thought I was just a young term level programmer? Or now we understand quite a bit about the type level programming. I don't think I could use it for anything serious, but like it definitely gives me the tools to go read other people's code and hopefully gain some more knowledge about how type level programming in Haskell works, you know, practically. So that's kind of exciting. I know all the terms, right? Like the vocab, basically. Okay, wonderful. Oh man, my computer was about to go to sleep. Hopefully that didn't screw up this stream. That's funny. Okay. This should be good now. And we are going to... So data definitions can be wrapped in the definitions quasi-quoter and run via the singletons function. The resulting splice, I don't know why splice is an interesting term for this, will be completely equivalent to our hand-rolled code above, including instances for sing, sing kind, and sing I. In addition, if the definitions have eq instances, singletons will also generate s-decide instances for them. Okay. S-decide is nominal equality for singletons. If two sings of the same kind are equal, S-decide allows us to use that fact. Recall the definition of A::, which is only constructible if A tilde B. Okay. The type A to void. This is very weird. I thought we'd get this stuff for free. I don't understand. Yeah, let me just write this and maybe it will make more sense. I'm not even sure. Stru percent equal stru where? Where? I don't know where I saw that. That's weird. Proved refl. Okay, and then I'll write some more stuff in here so that it makes more sense. Maybe. Proved Raffle. I have no idea what any of this means. Okay. So this S decide thing. Where does this thing come from? Am I creating it? Why am I creating it? I don't understand. I thought I got it. I don't understand where this is coming from. I think I have to define it. But I thought I was getting it for free. I thought that was kind of the point, but maybe it's not. Or maybe purposely there's being stuff left out. Decision a what? So wait, why? I don't understand. Why is it? This is already defined. Okay, so these things are already defined. That's the point. So I'm basically just putting them in here for my own knowledge. And this S decide thing is eq instance one level up, right? Okay. It's eq instances for singletons. So there is the version for of S decide for Boolean. So now we have an exercise 15 for I give instances of S decide for maybe. Okay, so instance S decide maybe why do I keep wanting to write S decide? I mean, clearly that's gonna have to be the case. Oh, it's gotta be S maybe? Sh maybe? Or is it supposed to just be maybe? Probably, it's just maybe. Oh, right. Okay, yeah, this is duplicate because it's already defined in the standard library. That's fine. We just need to see if it compiles. We could also just make our own just type, but I'm not going to play with that. So essentially we're gonna have S just a S just a prime equals So I think it's something like this. If we get two S-justs, it comes down to the comparison of the A types. If we get nothing, they're the same. If we get anything else, they're not the same. I wrote it here too, look at that. Decide. I don't know where that's coming from. B and D are nowhere, well, I mean, they're not that far away from each other on a keyboard, but still. Okay, let's see if we're right, but I think that's right. 15, 4. There's only one more exercise, by the way. Oh, I actually have to explicitly pattern match out the result, apparently. It's hard to know, like, if I actually have to do that because this doesn't type check. I mean, I'm not going to rewrite all of this by myself, so. But in the book, they have the following. Just case of proved raffle. And this was probably because the result of this, yeah, I think this makes sense. So the result of this is actually an S decide A. What I need is an S decide maybe A. So this left side is S decide A, the right side is S decide maybe A, and same is true for this one. So that's the reason you need this. That makes sense. But again, our type checker probably would have told us something like that. But we can't get type checking because we're defining a duplicate instance, and I'm not about to write all the pieces necessary to make this work. Although, actually, wait a second. Can't we just do the following? Hang on. No, I don't want that there. So just put primes. So let's just write this a little nicer. I mean, I guess that's nicer. It's kind of weird with this thing. Okay, so I need apparently empty case. Yes, standalone deriving. in patterns with scoped type variables. I probably need some sort of way to define that A is the right type. Is that correct? Probably. Let's see. CD. Um, hmm. Wrong way. Can I get it to... Oh, it seems to think that I need this. Okay, so add enough things and you can get it to compile. You just have to let um, your code actions go crazy. So apparently this will work. So can we modify this code to make this work? Maybe prime? S just prime, probably. S nothing prime. Now it's complaining again. Oh, it gives you that automatically, so that's kind of problematic. Right. So I can't do this. I want to see if I can do this because I would like to be able to. So S just is going to come from what? It's some kind of, it's a type family. Let's, we need, yeah. Basically it's this on the right. You might not be able to see all of it, but data instance sing a maybe prime. Oh, I can just copy and paste this more or less and put primes in there. Seems to be okay. Okay. Neat, I guess. We can just make sure that it isn't that GHC or HIE is broken. Wow. Okay, so anyway, there we go. There's the right instance for this, and we proved it. Now, what we wanted to show is that the following will fail. That was the point. And again, well, let's show that this actually fails. Relevant bindings. Well, it's hard. Oh, here we go. Well, that's not very helpful, but actual type. Oh, well, here you go. So this should be sing A1, sing B, decision A1, AB. So the result expected type is supposed to be that, but it's got some other type. So that's A2, A3 are just the wrong data types. So that's, I mean, it's pretty close to the error that you want. So what did we add? It seems to think that we need all of those. So anyway, the point is that there we go. We proved it. I guess we didn't really prove it. I just did my best to make it work. Okay, so that's it for the day. We did actually quite a bit of stuff. So we built some stuff using index monads. We built some generalized singleton types to do dependent typing. We used a little bit of the singletons library, and next we are going to do some dependent pairs. I don't really know what that means yet, but it says sigma types, also known as dependent pairs, generalize arbitrarily deeply nested either types parameterized by a type. The sigma types are the pair of an existential singleton and a type indexed by that singleton. Okay.